Check, check, check. 1, 2.
Doing the rounding up. I know. Ladies and gentlemen, good evening. Good evening. My name's John Lavery. For those of you who don't know, I'm the Secretary to the Royal Commission for the Exhibition of 1851. Before we get to the really good bit, we've got to do the housekeeping bit. And part of the housekeeping bit is, without looking, if people feel the need to move ever so slightly forward, there seems to be a slight gap. It's all at the back, and there's some spaces. If someone feels moved to move slightly further forward, our distinguished speakers won't feel quite so vulnerable. I'll leave it in your own time to do, but it might be something. Just move forward a little bit. That'd be really helpful for one or two spaces, so we sort of get a more even spread this evening. Well done. There's no points, but I am taking names for next year, so I will spot those people sitting deliberately at the back. Yeah. Just say, so the agenda this evening, as you can see, very much just a quick welcome. In a minute, I'll introduce our speakers, and then we'll go through effectively the presentation as is. We are actually recording this and broadcasting it for those people that want to actually have attended by Skype. So, Skype, by Zoom. Showing my age, so I apologise about that. Some of us were around at the beginning of this digital revolution. And effectively, hopefully, we will listen to the research of our completing fellows. Then we'll break for slightly more booze and something to eat and more networking, and then obviously we'll come back for the keynote address. Hopefully, I think that is it. Housekeeping, as I said, we're recording it, so if you do want to refer afterwards and have another look at it afterwards, Kat will have the details and she'll pass those to you. And I think at that stage, I'm going to introduce the proper host of the evening, who'll be looking after the rest of the night, so Professor Jim Al-Khalili, who's one of our Royal Commissioners. Jim.
Thank you very much, John. Skype. Okay, Grandad. Okay, Boomer, as my kids will say. Good evening, ladies and gentlemen. Very warm welcome to this evening's event, the 1851 Royal Commission's Alumni Science Evening. It's an opportunity, of course, to celebrate the achievements of both our current fellows, from whom we'll hear from shortly, as well as renew old acquaintances and make new friends, hopefully, from within the 1851 community. It's always a privilege to come back here to the Royal Society. I have the honour of being a Fellow of the Royal Society. I have no doubt that many of our 1851 Fellows will also one day become Fellows of the Royal Society, because you are all so smart. The Royal Society and the 1851 Royal Commission have so many common goals and enjoy very strong links. So it's wholly appropriate that we learn a little about some of the incredible research being undertaken by our fellows here, both past and who have tuned in via digital media, Zoom, not Skype. 3 of the Royal Commission's 5 core award programs, Science and Engineering Research Fellowships, Industrial Fellowships, and Industrial Design Studentships, are represented in this evening's program. I have to start by thanking Guy, Lucy, Banner, Daphne, Zach, and Jeremy from the 2023 and 2024 IDS cohort, and Dr. Alison Cribb, one of our current research fellows, for allowing their work and ideas to be scrutinized next door during our welcome reception. If you haven't had a chance to talk to them and look at their displays, then please do so in between the 2 sessions in here. From cortisol concentration detection through an exploration of time perception to mold sensors, their ideas and proposals are great examples of creativity, innovation, and design skills that are encouraged and developed within these programs. So I do encourage you to go and chat to them. Now, the next element of the evening consists of 4 presentations from our 2 senior programs. As usual, the challenge for the speakers is to encapsulate the complexity, significance, and excitement of what they're doing in about 10 minutes. And at the same time, make it comprehensible to those of us who are not experts in the field. This is wide-ranging areas across the whole of science, and so you may be an expert in one area, you won't be at all an expert in another. So it's by no means an easy task, but we all look forward to some fascinating topics, and I'm sure to learning a lot. I'm going to introduce each of our speakers in turn, and on completion of each presentation, there'll be a few minutes for questions. But before we start, I'd like to invite my colleague, Lord Karkar, the Commission's chairman, to say a few words.
Well, Jim, thank you very, very much indeed, in particular on behalf of the Royal Commission to you for having agreed to host this very important evening. And it really is a very important evening in the year of the Royal Commission, because we are deeply committed to ensuring that the community, which represents our current and our previous fellows and students, are able to come together with previous commissioners and all those who believe in the values and the vision set by Prince Albert some 175 years ago, remains relevant today. And it was a very powerful vision that saw the opportunity of taking science, engineering, technology, design, and applying it in the most effective fashion, driving the educational opportunity, developing people, ultimately to drive advancement in society, drive prosperity, and improve the life experience of our fellow citizens. And that's why all of you are so very, very important. Those of you who've been associated with the Commission through participation in our educational programs, those who are currently participating, have the capacity to have a huge impact on what can be delivered, will be delivered, and of course has already been delivered. This evening, we celebrate that alumni community, and thank you all both for being here physically present and also those who are joining us online. We'll hear, as Jim has told us, from some remarkable presentations of really outstanding work. And of course, there's the opportunity also to visit the displays of our industrial design students. And after the break, we'll hear from our keynote lecturer, Professor Philip Donoghue, and we very much look forward to that. But I'd like to use this as an opportunity just to emphasize two important initiatives of the Royal Commission which will impact all of us in the coming year. The first is the Growth Through Fellowship programme, which is a programme where we now wish to understand from our alumni community the impact of our educational programmes. How did you find being a student or fellow associated with the Commission? What impact has that had on your career? And what advice would you give us with regard to ensuring that we can consolidate the opportunities that the studentships and fellowships provide, not only in real time as they are being exploited, but far beyond that, both in terms of developing your own careers, but also in helping develop the careers and impact of others. And the second, of course, is the fact that we will celebrate the 175th anniversary of the Great Exhibition next 1st of May or thereabouts. And on that occasion, Her late Majesty had provided the opportunity for the first Prince Philip lecture to be delivered, and that will happen around about that time. And I hope that's an opportunity for many of those currently and previously associated with the Royal Commission to come together, to listen to what will be a very stimulating, insightful and motivating lecture, but also to attend our President's 10-yearly reception, bringing together the entirety of our community, which will be another opportunity for you all to gather, to meet each other, and all to reflect on how we can ensure the Royal Commission does more and more good, set by the overarching vision defined, as I say, 175 years ago by Prince Albert, but very relevant, in fact, more relevant today than previously, because what we're all interested in, has an impact potentially on the lives of every citizen in our country and beyond. Thank you all very much indeed.
Thank you very much, AJ, for those kind words. And of course, we are looking forward indeed to next year's 175th anniversary. It's going to be a really big year for the Commission. Okay, so let's get on with our first part of the programme proper. And we start with our first speaker, Dr. Magdalene Ho, who was awarded an industrial fellowship in 2022. She completed her master's degree in biomedical engineering at Imperial College in 2020, which included a placement year as a device research and development intern at Novartis in Switzerland. She then successfully entered Imperial College's CDT program and carried out her PhD research project with Convatec. Now, she was awarded her PhD just this January, so congratulations on finally getting a PhD. And as you can see, her presentation, Smart DNA, Super-plasters to Engineer Wound Repair. Mag Ho.
Hello, can you hear me all right? Okay, well, I'm very excited to spend the evening with you, and I hope I'll keep you entertained, and if not, just pretend. So wound healing is something that we're all familiar with, from the scrape of our knee to sometimes something more traumatic that could stem from a traffic accident. Regardless of the types of wounds, our body requires well-coordinated instructions from many types of cells and many types of proteins to heal efficiently. Our bodies produce a molecule called growth factors, which give instructions to the wound cells, telling them to regrow blood vessels, for cells to proliferate and migrate. So you can think of these growth factors essentially as instructions, as if you are trying to assemble a furniture. When you have the right instructions given in the right sequence, things generally work. But unfortunately, for some wounds, such as diabetic foot ulcers, they don't always heal. And oftentimes, it's because there are insufficient amount of growth factors at the wound site to give the right instructions for the wounds to heal efficiently. So it's like looking at an instruction manual, but with missing instructions. You might make it to the end, but it's a really good chance that you don't. So a strategy is to supplement these wounds with additional growth factors. They are currently being delivered through a gel or a spray, where you have to apply it many times a day for many days in a row. But it's essentially giving just one type of instruction over and over again. As you can imagine, it's not very effective. In addition to that, they're delivered with nothing to hold it in place. So as the proteins travel through the body, it might cause unwanted tissue growth, increasing the risk of cancer. So there's a real need for controlled, targeted delivery for efficient wound healing. So how can we give the instructions back in the right order for efficient healing? Can we create a material that can constantly sense the environment so that you can give instructions at the right time? To answer this, we turn to nature for inspiration. So tracing as far back to sea urchins 640 million years ago is the evolutionarily conserved delivery of TGF-beta1, a pro-healing protein. This delivery mechanism is still conserved in our bodies today. The structure is really simple. So you have a large latent complex structure that binds your pro-healing protein. Cells would then come along during the wound healing process to pull on the handle, causing the structure to uncage and release the molecule. Think of it like a helium balloon tied to the end of your wrist. If you pull to untie it, the balloon will be released. So we decided to make a synthetic version using single DNA strands. The single DNA can fold into a 3D structure to then bind pro-healing proteins of choice. You can then add a handle so that target cells can pull on the handle throughout the wound healing process, causing the DNA strand to unravel and release the protein. So here, we have traction force activated payloads, a system that can essentially release proteins when activated by cells. And it's very easy to make and scalable. You simply have to type the varying sequence of ACTG into a computer, and we have a machine in the lab that will synthesize the DNA for you. So then the million-dollar question is, does it work? So to test this, I seeded endothelial cells, the main type of cells and blood vessels, into a spherical shape and placed it into a collagen gel. In the collagen gel, I also functionalize it with traps surrounding this shape. And in this case, I deliver VEGF, which is a pro-healing protein known to initiate vessel sprouting. So as you can see, you do see very obviously endothelial sprouting. And when you look at the different control groups, so the control is just an empty hydrogel. The scrambled trap is essentially traps, but with a non-functional handle, so cells cannot pull on it to release the growth factor. And if you look across the different timelines, you do see that traps, especially at 24 and 48 hours, promote longer, thicker, and more sprouts, which is an early indication of vessel initiation and progression, showing that we were successfully able to deliver VEGF in a cell-activatable manner. So this is good news. Our next question was, can we completely eliminate the reliance of getting these proteins from the factory? Currently, they're being manufactured. They're very expensive to manufacture as well as store because they often have to be kept in cold chain logistics. Can we instead get these proteins from an accessible source at the point of care, like our blood? Our blood is filled with plenty of these growth factors, and with traps, we now have a good way to selectively attract the growth factors that we want and use it. So all we have to do is functionalize a wound dressing with multiple different types of traps, soak it in blood, rinse out the unwanted inflammatory cytokines that you might not want, and place it into a skin wound. And this is what happens. So after 10 days, cells surrounding the sponge, so cells surrounding the skin wound, starts to migrate into the sponge. And if you look more closely, you do see pretty good integration between the cells and the collagen sponge. For those that care, the skin is stained in magenta for F-actin, and cyan is DAPI for the cell nuclei. And if you look at the control groups, you do see increased cell migration towards the sponge, showing that traps wound dressings are able to promote healing skin. But if you look at the cross-section, that's when it really becomes obvious. You do see increased dermal integration between the skin, which is in blue, into the collagen wound dressing. And again, if you compare it to the control groups, we show that traps promote increased dermal integration and thereby promotes faster healing by 2.5 times. So to further validate this, we also did a preclinical animal study where indeed we showed again that traps decreased the wound size, increased healed tissue, and because we're able to do it in such a targeted and localized manner, and also able to harvest it from an accessible source, we can then use multiple types of proteins, which enables the use of up to 100,000 times less proteins compared to clinically existing strategies. And right now, I'm in the process of spinning this technology out from Imperial College London. So in case anyone in the audience wants to continue funding me, I am doing the spin out. So in parallel, and future exploration, or actually things that we've already done in the lab. Remember how I said in traps you can use different types of handles? We can attach different types of handles to target different types of cells. So in that sense, you can really start being the conductor of an orchestra to tell and instruct different types of instruments to work together to play a song. So in this case, it's delivering different types of growth factors to different types of cells so that they can work together throughout the wound healing process for efficient wound healing. And I want to end off by a fun collaborative project that I did with the University of Washington. Essentially, what we did was use light to spatially pattern traps into the image of my dog. So if you look at the input image, those are the original image, and the ones on this side is traps in the image of my dog. Thank you.
Thank you very much, Mag. That's a wonderfully clear presentation. You set the standard. Okay, so we have a few minutes for questions, so please raise your hand if you have a question. And we have microphones coming round for you. Don't be shy. Thank you. So we have the furthest away from the microphone, but excellent, but nevertheless. Oh, we all know you're there. Right, thank you.
Thank you for the presentation. You mentioned you're thinking of spinning this out as a company. What would be your strategy for spinning it out? And I should say we spun out from Imperial, so maybe worth a conversation afterwards.
That's great, definitely worth a conversation. So we will sub-licenses to wound care companies because we can attach traps onto their existing wound care products, so we don't have to reinvent the whole wheel. We want to go into skin wounds to begin with, but we can use traps to adapt it to other types of wounds like bones, hearts, and gums. So we want a sub-license so we can explore multiple applications.
I think that's very interesting. I think it relates to your question. Do you have a way to control the mechanical properties of your kind of sponge? Because you mentioned you can go into bone, and that's very, very interesting and very. If you can do that, that can be amazing.
So for traps, we can adjust the properties of traps, but the good thing about doing it for different applications is that we don't have to change the traps. We just have to change the material it's attached to. So in that case, we could use the sponge that we currently use and change its properties, but we could also use material that is already used for bones. So we're also looking at bioglass for now.
Someone from the other side of the hall, maybe? To make use of those microphones?
Story of my life.
Hi, really good work, really cool. So I guess in terms of, it's going to sound unusual, but sort of how fresh does the wound have to be? Is it one, could you use this technology in something that's slightly older in terms of a wound, or does it have to be very, very fresh?
So in theory, you want to use it at a stage where it's proliferating. So if it's an old wound, usually what would happen is that you would have to debride the wound to make it a little bit fresher, and in that case, you can use it on it. Thank you.
Thank you. Okay, we have our last question here.
This is more of a comment, but as a clinical nurse, I think this is really exciting for more tissue viability and being able to provide that level of care to a patient so they can heal faster in a way that's, I suppose, taking them out of hospital and being able to be cared for at home. It's really, really interesting to see and really fantastic work. Thank you. Congratulations.
Thank you.
Right, well, I think we should end it there. So let's thank Mag Ho again. For
Thank
lovely
you.
Okay, so our second presentation is also a 2022 Industrial Fellow, Matthew Diable. Matthew is a graduate of the University of Liverpool with a master's degree in chemistry and has also undertaken roles at Lubrizol and Thermo Fisher Scientific to further his experience in chemical research. A founding member of Polymer Mimetics Limited, a newly formed joint venture between Scott Bader and Liverpool University, Matthew's research has been focused on the development and commercialization of a proprietary polymer technology for various photocuring applications, predominantly in the area of 3D printing. I'm sure we can look forward to a fascinating presentation from him this evening, which is entitled New Polymeric Photoinitiators with Improved Migration Stability for Safer Photocuring Technologies. Over to you, Matthew.
Yes, thanks very much for the introduction, and thanks again to Mag for the wonderful presentation. Certainly have set a very high standard for me, thank you. I'm going to try and overview a part of my PhD research that has been on the development of polymeric photoinitiators for light-activated 3D printing technologies and products. I've tried to come at this from quite a high level. So, one, obviously there's confidentiality challenges for us working in the industry, but two, obviously I appreciate we're not all chemists in the room. I don't want to lose anyone during this presentation. In fact, you could possibly say I've tried to keep this light on chemistry. Anyway. Light-activated 3D printing, or more commonly known in the field as VAT, photopolymerization 3D printing, is a process that relies on light to fabricate complex and customized 3D objects from a reservoir or a vat filled with light-sensitive liquids, also known as photocurable resins. It's a £5 billion global market, and it continues to grow each year. However, what is restricting growth is some serious material challenges, and as a result, new resin development is critical in order to achieve key performance and safety targets. Photocurable resins predominantly consist of reactive oligomers and monomers, which react together in the 3D printer to form your solid object. However, there are other quite critical low-loading components of these photocurable resins, with photoinitiators possibly being the most critical part. So these are the light-absorbing components of your photocurable resin that basically take the light from the printer and convert it into reactive radicals, which then can initiate the reaction of your reactive oligomers and monomers. However, many current commercial photoinitiators suffer from common application restricting issues. I've listed a few here, so these include migration of toxic residual photoinitiator and photoinitiator-derived components from the 3D printed material, of course leading to both performance and safety issues. You've also got toxicity of many small molecule photoinitiators and the ever-increasing regulatory pressures in this area. And you've also got many associated formulation challenges. So, for example, a lot of the small molecule materials are powders. This can be challenging to actually blend them into your 3D printing photocurable resin during an industrialization. This is a hot topic in the literature, and a lot of newly developed photoinitiating solutions really struggle to balance four key industry requirements. And this is performance, reactivity, compliance or safety, and cost or industrial feasibility. So, in light of this, part of my PhD has been looking at ways to overcome these common issues. And one successful approach that I have found is through the modification of a proprietary polymer technology that was developed recently by Professor Steve Ranard at the University of Liverpool, and it has since been exclusively licensed to my company, Polymer Mimetics. So what we've done here is we're taking relatively low-cost, commercially available chemical feedstocks and using the principles of the highly scalable proprietary polymer technology, converting these into high molecular weight, highly branched, multifunctional polymers that are littered with covalently bound photoinitiating groups. I think a good analogy of these materials is a large oak tree, whereby the branches are representing your functional backbone in these materials, and the pendant leaves are representing the covalently bound photoinitiating groups, which basically will absorb light from your 3D printer to initiate the chemical reaction and ultimately form your 3D object. So these macromolecular trees, you could call them, possibly more technically put as hyperbranched polymeric photoinitiators, have been found to have highly desirable properties for use as photoinitiators within 3D printing. So for example, they combine high molecular weight or low toxicity with relatively low viscosity, high solubility, and high photoinitiator functionality and accessibility. And this is all due to the highly branched or the hyper-branched architecture of these materials. So perhaps the most attractive, or one of the most attractive aspects of this new technology is its versatility. And this arises from the wide amount of highly available commercial chemical feedstocks that we can use in this process. So for the chemist amongst us, I have included a few chemical structures for us. So these are some of the photoinitiator types that we've been able to access with this new technology. So these include your highly efficient type 1 photoinitiators, perhaps most importantly based on acylphosphine oxides, which are commonly used in 3D printing processes, and also some one-component type 2 systems whereby your photoinitiator or your light-absorbing moiety is bound to the same macromolecule as the required co-initiator, obviously supporting both handling and ultimately performance. We can also easily tune the polymer properties of these materials through careful selection of our feedstocks, ultimately directing the backbone and chain end functionalities of the materials. So as an example here, we can easily tune the solubilities of these materials from water-soluble photoinitiators, which are of benefit in the ever-growing area of hydrogel 3D printing, all the way up to highly hydrophobic photoinitiating materials, which can be of particular benefit when you're immersing your 3D printed object in an aqueous environment and you don't want the photoinitiator to leach out into it. So, for example, in dental 3D printing. We can also easily tune the properties or the physical properties of the polymer to aid with handling and performance. So, for example, we can produce flowable liquids with extremely low colour. So I think at this point it would be fair to ask me, so what? So the vast material scope, the ability to access a wide range of commercially feasible photoinitiating solutions effectively provides the opportunity for the next generation of commercial photoinitiators, ultimately to support the continued growth of VAT photopolymerization 3D printing. So we've been able to find an effective balance with these photoinitiators of product safety, high reactivity, and application scope. So as a few examples, we've been able to demonstrate the lower product migration of these photoinitiators from the 3D printed part, owing to the high molecular weight compared to many other photoinitiators used today. And this obviously leads to higher performing and safer products. You've also got high photoreactivity under LED wavelengths, owing to the fact that you've got a plethora of accessible photoinitiating units on these materials, which can obviously support the rapid and efficient 3D printing of materials. And you've also got wide formulation scope, whereby these materials are soluble across a range of monomers and oligomers that are used commonly within 3D printing, ultimately enable us to impact a wide range of applications. I believe that these materials will help to fully unlock 3D printing, in particular in currently restricted areas. So shown here, you've got the likes of your dental 3D printing, your biomedical 3D printing, and your 3D printing of wearable devices, all of which require the use of high-performing, sustainable, and compliant photoinitiating solutions in order to be used. Of course, with this in mind, I think it's important to highlight that the development of these photoinitiators have actually provided us with the opportunity to impact way beyond 3D printing in applications that also demand high-performing and safe photoinitiator solutions and products. So these include the likes of packaging inks for food, for medication, for cosmetics, UV coatings, inks and varnishes, particularly those requiring human contact. You've got UV adhesives, particularly in the growing area of wearable devices. And you've also got conventional dentistry. All of these use very similar chemistries to those used within VAT photopolymerization and 3D printing. One key thing is that, going back to the versatility of this technology, we can easily tune these materials to suit the specific needs of each application. So I just wanted to end with how the Industrial Fellowship or the Royal Commission have helped us to ultimately get to this position. So of course the financial aspect has given me the opportunity to look at a vast range of technologies and products using the proprietary polymer technology. And this is including, but certainly not exclusive to, these polymeric photoinitiators. This has ultimately accelerated new IP development. So a recent example of this is that we've just filed a patent on this photoinitiator technology, hence the ability to be able to talk a little bit more about it. Likewise, the external disclosure, so the attendance of key 3D printing events across the world, obviously has got the word out for us and ultimately resulted in quite significant commercial interest in this technology. And all this has led to plans for us to industrialise and commercialise this technology in the near future. Of course, without the support of the Commission, I don't think all of this would have been possible within the time frame of my PhD. So I'd just like to thank all involved in this project, including my colleagues at Polymer Mimetics, in particular my industrial supervisor, Dr. Paul Finley. Of course, the founder of the core polymer technology, Professor Steve Ranard, who is my academic supervisor, and his group at the University of Liverpool. The 3D printing team at Scott Barder, and of course, finally, the 1851 team and peers for the PhD funding and support, and also the opportunity to talk about this tonight. Thank you very much.
Thank you very much, Matthew. Okay, time for a few questions. Yes, right at the back.
Hello, thank you for that. I'm a chemist, so I really enjoyed it. I've got two, if I may. The first, you also mentioned you had a background in Thermo Fisher, so I was interested in how do you prove, if you're able to say, that you don't have migration of the photoinitiator? Do you do some sort of aging, and are you able to talk about the techniques you might use to prove that?
Yeah, I think I can just about do that. So my work has predominantly been in the 3D printing space. So this has involved 3D printing materials using these photoinitiators, along with materials printed with commercial materials, including commercial polymeric materials. We then go on to immerse these within common organic solvents, so the likes of methanol, chloroform, hexane, providing almost beyond worst case scenarios for many applications. We can then take the extracted media, so the solvents, strip the solvents off and do analysis, either by HPLC or quite importantly, in the case of the acetylphosphine oxides, ICP analysis, so you can look at the phosphorus leaching. And we've found that these materials are particularly lower phosphorus leaching compared to the likes of your common photoinitiators like the likes of TPOL that are used in 3D printing.
That's great, thank you. And a second, if I may, you've talked about packaging and some health applications. Do you sort of see anything in terms of aerospace and defence too here?
I mean, there is possibility. I think it's important not to try and shove the technology into as much as you can and focus on the areas that are actually demanding these sustainable and compliant technologies. And of course, the likes of dental and biomedical are key examples of that.
Thank you. One last question here. Yes, in the front.
Hi, another chemist here, apologies. Polymer chemistry is notoriously sticky and messy. Did you have any particular frustrating and memorable moments in the labs?
I've had plenty, yes, I've had plenty. It's made me the person I am today, I would say.
Great work, well done.
Well, let's thank Matthew again.
I should say, if you do have more questions for our speakers, we do have time in the supper interval, so do please seek them out and ask them questions if you didn't feel you wanted to ask it publicly. Don't know why I got my phone out of my pocket. It's my notes I want. Okay, so our next presentation is by a 2022 research fellow, Dr. Tim Hageman. Tim is a departmental lecturer at the Engineering Science Department at the University of Oxford. Prior to this, he was a research associate at Imperial, having obtained his PhD at the University of Sheffield, developing multi-scale models for poroelasticity. His research focuses on developing novel finite element schemes for a wide range of multi-physics and multi-scale problems, among which hydraulic fracturing processes within ice sheets, hydrogen embrittlement and failure of metals, and corrosion processes, and he's going to expose a little of his thinking this evening. His presentation is entitled An Engineering Approach to Modelling the Collapse of Ice Cliffs. Tim, over to you.
Thank you for that introduction. Indeed, today I'm going to be talking about my research related to ice sheets. People probably all know what ice sheets are, large bits of ice on Antarctica, Greenland. And these typically are modeled using ice sheet models. An example is shown here on the left, where these amazing models are able to capture a whole continent, slowly capturing the melting ice, modeling how it sort of disintegrates and it slowly creeps back over many years to decades. These models are absolutely amazing. They can capture a whole continent, and they have a resolution of about 5 kilometers. So one downside of these models is they don't capture anything that happens below 5 kilometers, which, as you can imagine, has some disadvantages. On the right here are satellite observations from 2002 from the Larsen B ice shelf, which was located in Antarctica, where you can see that small-scale fractures disintegrate these whole ice sheets in the span of 2 weeks, with these fractures being typically smaller than 5 kilometers. So what you see here is the ice sheet disintegrating. It's about to give you a sense of scale. On the left side, you can see mountains. This is about twice the area of London, disintegrating in 2 weeks' time, and nothing related to this is captured by existing ice sheet models, which is a bit of a gap in knowledge, especially considering that ice sheets are becoming more unstable over time. So it might be important to have better models able to predict this type of failure. So glaciologists have known that this is a problem for a long time, so they've tried to solve this. Why do they need engineers? So to start off with, glaciologists typically model ice as a fluid. It essentially slows downhill over many years, and if you think of a fluid like honey, you can't really fracture it. The most you can do is just pull it apart, and eventually it just splits into two, which is also the approach taken for modeling ice sheets. You don't do anything related to shear fractures. You just, if you pull the ice far enough apart, it fractures, ignore everything else. with the sort of state-of-the-art small-scale glaciology models obtain the results shown here in the middle, where you can see fractures just developing based on being pulled apart. And if there are any engineers in the room, which I suspect there are many, you can probably see this type of failure is not quite looking right. If you have any type of cliff, you would expect the top to slide off. You don't expect a nice cube to fall off straight away. And in this case, it wouldn't even fall. It's still nice and square. So this has also been shown many times over by people doing particle-based simulations, mostly aimed at cliffs and soils mechanics, where they see sort of the cliff failing and sloping and falling over instead of these square fractures happening. However, glaciology over the last 25 years or so has adhered to this assumption that fractures are only due to tension, ignore everything else, we can't capture that. So we want to understand better how does ice actually behave. And for that, I show two examples here. On the top, if we assume ice is a granular material, at the bottom, if we assume ice is a brittle material. These are sort of the two extremes. Assuming ice is just a bunch of loose snow, and assuming ice is basically an ice cube, it's glass, if you drop it, it shatters. And as you can see, these two small assumptions, only in capturing how different fractures behave, same material properties otherwise, result in vastly different behavior. The top result is good. If ice sheets behave like that, we just have fractures on the surface, the cliff is stable, we're happy. The bottom result is less good. If ice behaves like that, somebody would just hit the front of an ice sheet with even a hammer or a ship or any type of small impulse, and it would just shatter like a pane of glass. Here is a result of like an ice sheet 1 kilometer long, just disintegrating within seconds, due to me just applying boundary conditions to the front. Neither of these is realistic. The top one, probably not the correct type of failure. The bottom one, we know ice sheets exist, so probably also not correct. So can we take a more engineering approach to this? Instead of just moving to an ice cliff, can we start at the smaller scales and slowly work up from this? And here I'm showing two results from literature. On the left and on the right, essentially triaxial compression tests. Take a 30 centimeter cylinder of ice, compressed on the top and bottom, see how it fractures. And here we see both behaviors. On the left, if we don't compress it from the sides, just from the top and bottom, it's brittle. Essentially, it just shatters instantly. If we apply some pressure on the sides as well, it's ductile. It's more sort of like rubber or like honey that's being compressed. It just sort of shears apart eventually, but it's very much sort of like metal. So we have these two behaviors in ice. And what my research has focused on is, can we capture these two behaviors and then apply it to ice cliffs, predicting failure? So here are some results. Here is the brittle behavior. As you can see, you compress the ice from the top and bottom, and it just shatters into 1,000 pieces. On the left side, I'm showing the displacements, nice colorful pictures. On the middle, I'm showing simulation results showing the fractures, where it's blue is intact, red is broken. And you can see it behaves like essentially you expect an ice cube to behave. It just shatters into pieces as soon as you apply any force. However, with computational modeling, we can also calibrate our models to capture the other extreme. Now we have ice being very ductile by just applying extra pressure to the sides. Where you can see, okay, instead of now shattering, it behaves more like metals or like traditional engineering materials, where you get ductile failure, it fails over time. It's essentially more stable than when you just have the brittle behavior. And the nice thing is, these computational models have been calibrated against experimental data. So we know, okay, ice actually behaves like this. It captures experiments. If you compare the results to the experimental results shown on the right side, you can see, okay, the fracture pattern, it's not exact since we're dealing with natural materials, but it's sort of like in the right ballpark. So we can expect, if we use these models, ice behaves this way. And the nice thing is, we can also then, since it's a computational model, just multiply all dimensions by 1,000. And instead of simulating small test samples, we're now simulating ice cliff failing, where you can see, okay, this is more realistic type of failure. You still get the mode 1 fracture, like the tensile fracture growing at the top of the surface. Essentially, you can imagine the ice cliff just wants to topple over. But at the same time, the ice is quite heavy. This is 200 meters high ice cliff. So you also get, instead of the toppling over, you get the sliding downwards motion, which both combine together to predict ice cliff failure. And through these models, we've investigated how stable are cliffs if you apply water to the fronts. Here on the right is a lot of the experimental data points and field observations plotted with the nice colorful markers. And the two colored regions, the red one and the gray one, are approximations of this model, whether cliffs are stable or not. So in the red region, they're stable. Gray region, they're stable as long as we fudge the material parameters a bit. In the white regions, cliffs are unstable. And as you can see, this model, calibrated on experimental small-scale data, captures quite well what happens in reality. However, this is only half the picture. Ice has another annoying behavior in that it can melt. If ice melts, you have water on the ice sheets, and as everyone who's gone outside in the winter knows, water is heavier than ice, so the water wants to go down, ice wants to go up. And we can also capture that through computational models. So here are some results for if you have a lake on top of the surface of the ice sheets. The water will essentially pressurize the lake. It will pressurize any fractures that are present. And so essentially, just by melting at the surface alone, tunnel its way to the bottom of the ice sheets, which you can imagine is quite bad. And as soon as it reaches the bottom of the ice sheets, the bedrock is typically not that porous. So you have water piling up there, essentially forming a thin sheet of water at the base, where you lubricate the ice sheets, and it will just essentially slide over water instead of sliding over rough rocks, quite accelerating how fast ice sheets move downhill. And then finally, to show off some more recent results, we can combine these two. So now let's assume we have fractures, which are shown at the bottom here, but you have also the surface is melting. So now you have meltwater at the surface that wants to go down. You have an ice sheet that's unstable. And as these two combine, you see now the ice cliff fractures, and you get hydraulic fractures propagating downwards from the right side, which create a sharp cliff. However, then you have a sharp cliff, which is the conditions we started with. So then further to the left, you get the water pressurizing the ice, creating hydraulic fractures that propagate downwards, which then again creates a sharp cliff. So to the right, you get more fractures that pressurize and propagate downwards. Essentially, these simulation results here span a simulated time of 10 minutes. And in those 10 minutes, the ice sheet has disintegrated a kilometer backwards, which captures quite well the unstable behavior that's also been observed at some places in Greenland and the Antarctic. Of course, these are still 2D simulations. Much more work is needed to translate this to 3D. You can imagine in 2D, a fracture going downwards creates 2 blocks of ice. In 3D, there's material in front and the back. Might behave completely different, but at least this captures quite well the instability mechanisms that are currently not captured by large-scale ice sheet models. And with that, I would like to conclude and thank the 1851 Commission for providing funding for the last 3 years. My background was not in ice sheet modeling, so it's been quite a journey to go into this field and apply applications from like geoengineering and fracture mechanics to ice sheets. Essentially, take the opposite approach as all of glaciology, starting small and then slowly growing out my model to capture big cases. It's just not typically an approach taken. So I'd like to thank the Commission for funding this research for the last 3 years. And also, I would like to thank my research collaborators who've essentially taught me glaciology and dealt with my overly computational mechanics point of view. And if any questions, happy to take them.
Thank you very much, Tim. Okay, time for questions. Yes, in the middle.
Thank you, Tim. It's a fantastic presentation. I'm a structural engineer and I like ductility. So just curious, in your model, where does the ice behave in a ductile manner and where does it behave in a brittle manner? Is it in the center? It's quite ductile because there is all this triaxial pressure and then the corners are brittle. Is it this way or?
It's essentially 2 different types of behavior. You have the failure of the ice itself is brittle. So the fracture mechanics is in a brittle manner. If there's enough tensile stresses, it breaks. And then if under shear stresses, it's ductile. So there you get shear bands forming. And then those shear bands transform the stress states to then eventually reach the place where the fracture due to accumulated damage. It's essentially under shear stresses, it's ductile. Under tensile stresses, it's extremely brittle.
Okay, I see. Thank you very much.
Okay. More questions? Yes.
You talked at the very end about how your simulations are in 2D. Yeah. What aspect are you most worried about in the generalization to 3D? And what do you think can still mostly hold?
Most worried about in the sense of expanding it to 3D or like phenomena that can happen? Most worried about expanding it to 3D is especially the computational cost. These ice sheets need to be, to capture these fracture patterns, I'm using a resolution of 0.5 meter sized elements for like 1 kilometer long, 200 meter thick ice sheets. Expanding that to 3D, there are some computational cost challenges with that. So currently in the process of sort of slightly simplifying my model. Maybe I don't need to capture it at 0.5 meter resolution. Maybe I can get away with 2 meters, which make it quite a lot cheaper. And from a physical perspective, I'm sort of hoping that by expanding it to 3D, it becomes less binary. Currently, it's either hydraulic fractures propagate downwards and it becomes unstable, or hydraulic fractures don't do anything. If you have material in the front and the back, it might be that hydraulic fractures just essentially do a rounded sort of bite out of the ice sheets, and then it's stable because of like 3-dimensional stresses and mountains on the side stabilizing it. So it's more like getting it more realistic and getting it hopefully more stable.
Thank you. Okay, so let's thank Tim Hageman again. Okay, so our final presenter in this session is Dr. Al-Khalili, who's also in the final stages of his research fellowship. Alex is a PhD graduate of Texas University, who then undertook a master's and PhD in astronomy at Texas A&M. Currently a member of the Department of Physics at Durham and a researcher in the Institute for Computational Cosmology there. His 1851 project title was Constraining the Nature of Dark Matter with Galactic Halo Substructures. So as he approaches the culmination of his research, we're asking him to share a little of his work with us this evening. His presentation is called The Tangled Web Surrounding Our Galaxy. Alex.
All right. Thanks, everyone, for joining this evening. And on a personal note, thank you, Jim, for being inspirational within the field of astronomy and for also being the expert panelist on my review. I remember it well. So today I'm going to talk a little bit, we're going to expand even further out than we have been this entire evening, and I'm going to talk a little bit about galaxies and how they form and sort of tie that into the nature of dark matter, which sort of evolved. It wasn't exactly what I wrote about in my application. However, I think we'll all be satisfied with where we went. So this picture on the tile slide is a real image from the Gaia satellite that took essentially pictures of stars within the Milky Way. So we see essentially the Milky Way, the galaxy that we live in, is sort of spread across the center. If we sort of went outside and tried to go to a very dark, a dark site up in Scotland, not necessarily right outside in London, you'd get some sort of image that's like this. So this is sort of, we can see the Milky Way sort of spread around, covering up a good chunk of the sky. This particular image is taken from the southern hemisphere, and you can tell because there are these two clumps of stars that are sort of relatively large, and you can still see them with your naked eye. And these are in fact actually satellite galaxies of the Milky Way, so smaller galaxies that are orbiting around the Milky Way. So already in our night sky, we have, if you go to the southern hemisphere, where you can see this, you already have some picture of what I'm going to try to grapple with sort of what's going on, not just in our Milky Way, but sort of in the outskirts. So this is a way that we can, see this sort of structure going on already within the universe, and civilizations going back to ancient times, have sort of, especially in the southern hemisphere where you can see these two galaxies, have sort of like, this sort of enters the lexicon, like the history, and people write legends about all this stuff. If we take a step back and try to sort of analyze, okay, how does Alex think about all this stuff? Usually it's something like this. So what I'm about to play is a simulation of a galaxy sort of forming over the course of cosmic time. And what's shown here are in particular the stars that are in all these galaxies. And so a galaxy like the Milky Way has accreted a whole bunch of smaller galaxies that we call satellites, just like the ones that we were seeing in the southern sky, these Magellanic Clouds. And as time sort of evolves forward, these smaller galaxies accrete onto our larger galaxies, something like the Milky Way, and they disrupt due to the stronger gravitational field that the Milky Way has. And so over the course of cosmic time, you get galaxies that accrete, disrupt, and form these structures and streams of stars all across the sky. And so you have things that are accreted very early on in the history of the Milky Way that aren't sort of easy to identify. They're all sort of mixed up in this sort of tangled web. You have things that accreted relatively recently and are losing stars actively, forming long stellar streams. And you have sort of intact satellites, things that accreted onto the Milky Way host that haven't disrupted all that much. If we look at the real universe, the real galaxy, and sort of you can see this in the night sky. This is sort of an astronomical image of this sort of thing going on. So here, I've sort of, or my colleagues have sort of reprojected the Milky Way. This is one way that you can do this. We still have the night sky. That's the sort of big band. And if you look at certain areas of sky and try to color, okay, most of the stars here have some sort of distance associated with them, and I color code by that distance. You can actually see these sorts of structures that are sort of emerging. We can see this in the actual night sky. So this band that's sort of coming up and then down that changes color is green over here, is orange over here. This is one of our largest stellar streams. This is called Sagittarius because the core of this galaxy is actually in the Sagittarius constellation. And then within the sort of weird, we actually call this the tank. The survey, the dark energy survey, the data here is much deeper and much more better calibrated. You can actually see maybe individual streaks that correspond to smaller objects that you can see. And all these streams, astronomers love to like name their things in the way that it'll evoke the most emotion. If you've heard of the baseball movie Field of Dreams, this is the field of streams that sort of surrounds the Milky Way. Now, one of the ways that we can use these streams, these accreted structures as they disrupt, are actually essentially as like a collider between two galaxies, and in particular, a collider of their two clumps of dark matter. So I haven't said dark matter yet the whole talk, and that's okay. We're gonna take a very surface level here, again, 10 minutes. But each galaxy sort of forms and is embedded in some sort of halo of dark matter. It's denser in the center and less dense further out. I'm currently employed at Durham University, and we are contractually obligated to color our dark matter as purple. So that's what's going on here. And if I add sort of the same picture that we were seeing earlier, where you accrete a whole bunch of systems, you can imagine that these satellite galaxies, these smaller systems, are also embedded in their own slightly lower mass dark matter halo. And this is true for many of the satellites that are sort of orbiting around the Milky Way or Milky Way mass systems. And even the larger of these satellite galaxies can have systems of their own, smaller satellites. All of these galaxies come in, they form, they're embedded in some sort of dark matter halo. And so as they're orbiting around their main host and within all these smaller things, this is basically like a whole bunch of like these spheres of dark matter are interacting and colliding with each other. And so you can actually sort of come up with some sort of interesting tests of the nature of dark matter this way. One of these ways is to sort of analyze, okay, once my galaxy merges into my smaller galaxy merges into this sort of larger galaxy, the distribution of debris will change if I change the nature of dark matter. So on the left here, I have some distribution of this debris that is what we'll call the normal dark matter. This is the dark matter that typically is simulators use in sort of the standard model. And on the right, what these simulators did was they said, okay, what if I change the nature of dark matter so that my dark matter particles can scatter off of each other? And essentially, once I throw my smaller galaxy, if my dark matter particles can scatter off of each other, they'll disrupt easier. Your dark matter, as it's flowing through you can kind of imagine it as flowing through some medium, and it'll disrupt easier because it's sort of flowing through this wind. It's actually the same thing that's happening when your dog sticks his head out of the window. This is what your satellite galaxy's dark matter is feeling as it flows through the medium that is the Milky Way's dark matter. So this is the easy way to sort of understand what's going on here. So up until this point, I've actually not talked about my own work here. And so I have three sort of over the course of my 1851 fellowship, I've sort of studied this phenomenon in some of these simulations, and I was coming up with, okay, what are sort of some three examples or lessons that I sort of learned throughout that process? So one of those, so I went through and in these sorts of simulations, the same type that I showed earlier, the sort of video, I went through and identified and counted all the streams. And then I compared that to both the Milky Way, the streams that we observe around the Milky Way, and to a different simulation suite. So I did this for this blue shaded region that's labeled Auriga. That's one particular way to simulate the universe. And I compared that to, there's a similar simulation suite called FIRE, different collaboration. That's sort of the most comparable version of doing this. And if you just count the number of streams and their stellar masses and compare those between FIRE and Auriga actually disagree here. And in a way that's like genuinely interesting. So this is sort of suggesting if we counted the satellites around the Milky Way and galaxies that are like the Milky Way, and did that in a full and complete way, that we should be able to distinguish between Auriga and FIRE this way. So that's already interesting, this discrepancy. Then you'll notice the Milky Way is way down there, right? Way fewer streams than what is in FIRE or Auriga for that matter. But that actually ties back to the importance of sort of mock observations of these things. So as a stream disrupts, you can see the core of the galaxy because that's where most of the stars are. But the sort of tidal debris, the part that's actually disrupting and forming a stream, is much harder to observe. You need to go to way deeper imaging. And that can maybe explain some of the discrepancy between the Milky Way observations that we have and FIRE or Auriga, that discrepancy we saw earlier. What this is suggesting is that there are either way more streams that are out there for people who study the Milky Way to go find, or that all the models are wrong and we need to revisit everything entirely. This is just an animation of going deeper and deeper imaging. You can see eventually you can see the sort of the structure that sort of fills in. Okay. Another lesson is that this tangled web, which sort of was originally meant to say, okay, you have all these streams that can sort of crisscross around each other and have this tangled web of streams forming around the Milky Way, actually runs even one layer deeper than everyone sort of thought. So again, coming back and highlighting that you can have, the more massive satellite galaxies can have systems of their own smaller satellites that are, as a system, orbiting around the Milky Way, you can actually get those smaller satellites disrupting around their more massive host. So here, the sort of contours in the center are the satellite galaxy of our Milky Way mass host, and the stream that's sort of disrupting around that satellite is a stream not disrupting around the main Milky Way, but around this smaller satellite galaxy. And so the sort of tangled web runs, even deeper. You have streams of satellites or things like that. And this may even be able to help us answer questions like, what's the smallest galaxy that can form? Or what's the smallest structure that can sort of exist within the Milky Way? And how does that tie back into, again, the nature of dark matter? The last sort of case example or lesson that I learned was that building a space telescope is hard, it turns out. And more importantly, more to the point, planning for a space telescope is really hard. So, sort of mid-2024, I had published this paper that was all the streams that are in Auriga, and this collaboration that's trying to build a space telescope called Arrakis. If anyone's a Dune fan, yes, it's a Dune reference. That's trying to image not just the Milky Way, but other galaxies and try to find all of their streams. And they saw my paper about the streams around these Auriga galaxies and said, hey, Alex, can you make predictions for what Arrakis will see? So here what I'm showing is one of these galaxies that I studied earlier. This is, again, the Auriga galaxies. The left is just sort of viewing the galaxy sort of edge on, and the other one's face on, so seeing the spiral sort of like this as opposed to on its edge. And this imaging that I'm showing here is how much structure you can see if we are only imaging this galaxy from the ground. So you can imagine, because the sky exists and things like this, you see less than what's actually out there. But ESA willing, in all these cases, I'll say when Arrakis launches in 2030, and then takes data of Milky Way mass galaxies that are extragalactic, we'll go from this sort of imaging to a much deeper imaging, a much more complete understanding of how these galaxies are disrupting, how these satellites are disrupting around Milky Way mass hosts. And again, we're very early days in this, but we actually think that we can say things about this dark matter, these interactions, this nature of dark matter question with Arrakis. The other thing I learned is that building a space telescope is hard. Convincing ESA to fund a space telescope is hard. But if you're going to do it with a Swiss collaboration, because the views that you can get at collaboration meetings are amazing, stupendous. Okay, so that was a bit of winding path through the things I've been thinking about. Again, I would very much like to thank the Royal Commission for funding all of this work. In particular, what I proposed, if you actually go back and read through the meat of my proposal, is very different from what I actually ended up studying, or at least that's how I feel. People told me that it's not actually. But a lot of that came from sort of a weird path of collaborations that didn't work out, and part of what helped was sort of the foundational support that the commission had that gave me the freedom to abandon this project that wasn't going to work out due to faulty collaborations, and instead go on to this other thing that I think was very, very useful. And then my last slide is just the collaborators that I had in my day-to-day experiences. The first row are people who, this isn't strictly true anymore, but at least at one point when I made this slide, don't have permanent positions. The lower row are the people who do have permanent positions. And then all the logos in the corner are the observational collaborations that have let me sort of sit in on their telecons and say, oh, you can't quite say that, or there are models here, you should test them, or things like that. So yeah, so this is the network that I had as I was doing this. That's all I have.
Thanks, Alex. Thank you very much. Okay, some questions? Don't be scared. Okay, I had to do the obligatory. You knew it was coming. So, my one question was going to say, what does the acronym ARACA stand for? But I won't ask you that.
It's something convoluted. I can't tell you. There's an Arrakis website. People can go to it. It's not even spelled out on the homepage. You have to navigate to like the mission because we're embarrassed at how convoluted the acronym is. Astronomers are very good at doing this. Yeah.
You said astronomers have good names for things. I mean, normally it's just letters and numbers, right? For stars and galaxies. I mean, that's field of streams is pretty good. But my question is, so for Arrakis, if that project goes ahead and you're talking about 2030s, are you waiting for data before your computer simulations can be improved? I mean, you can run simulations presumably and put in different properties of the dark matter, but presumably you're waiting for the real data before you can say which simulation is most realistic.
Yeah, so that's a great question. So Arrakis, the collaboration I was talking about before, is, yes, a mission that will launch in 2030. That's in astronomer timescales of how long does it take to launch a mission, that's very short. But in terms of a postdoc trying to get real data, that's quite long. These other collaborations whose logos are here actually do have a lot of data that I'm working with them to compare the observations that they are seeing to simulations that are like the ones that I've been showing. So those data sets already exist, and we're learning what we can from those. Yeah.
Okay. Come on, guys. Ask him what dark matter is made of.
Please don't just make this be two astronomers talking to each other. We don't want that.
Fascinating talk. Thank you. I thought I'd just ask you. Said you've got models which don't agree with experiments, and you're basically not sure which is more right. So what's your gut feeling? Are we missing stuff, or are the models just quite literally millions of orders of magnitudes out?
Yeah. So I don't show this because it didn't work its way into the narrative of the talk. If you take the collaboration that I'm not a part of, FIRE, in this logo, if you take their simulations and account for this effect that we were showing before, where it's harder to see these tidal tails, these low surface brightness features, you actually do you're able to take FIRE and sort of push it down to where it's reasonably consistent with the white curve that's there. We didn't do this yet for Auriga. This is something that we want to do next. It was already a huge effort and 2 publications to get to this point, and we sort of tabled the mock observations for something that's in the future. But actually, if you account for the effect here, where it's harder to find these tidal tails, that accounts for most of the gap between the Milky Way, the current observations of the Milky Way, and the models. So again, more of the morphes. So that aspect is more of the morph streams to find, less of the or models are wrong part of the statement.
Okay. Any more last questions? Yes. They're all coming thick and fast now.
I'm not an astronomer, and I don't understand very much what you said. But when you were showing the simulation at the beginning, where you were going through all of time, and it's sort of stirring, and gradually you've got all this stuff coming together, and you can see the streams forming and then sort of almost dissolving and all that sort of stuff. This one, it struck me that it looks a lot like sort of liquids being stirred, and that extra little blobs of a different liquid are being added. And I just wondered if you, beyond the sort of simulation here, you kind of translate other materials and liquids. Like, so I guess my question is, do you use other kind of media to sort of predict what you might see in these, like, real world, like on the earth kind of materials, just to sort of compare with your simulation? Does that make any sense?
Yeah, for sure. So I don't show this here, but included in these simulations are also things like gas physics and how gases interact with each other and things like that. So the same sorts of numerical tools that people use, for example, to study how one person sneezing can propagate through an airplane. It's the same physics and often in the same numerical tools like Lagrange meshes and other things that people talk about. It's actually the same sort of computation going on under the hood. So yes, in a word.
But is it basically just Newtonian gravity that's the force that's causing that turbulent flow?
For the stars, yes. For the gas, you have collisional physics and things like that. Yeah. But for the stars, because the stars don't collide with each other. They don't care about interacting with each other. Yes, that's mostly Newtonian gravity.
Okay. I think we probably should draw this to a close, and we thank Alex again for his talk. And so this concludes this element of the evening. A huge thanks to all our presenters for the way you dealt with your questions and for the fascinating set of presentations, which could not better demonstrate the quality, depth, and range of the work that our fellows are engaged in. So we wish you all great success in the completion of your fellowships and, of course, in your future careers. Now, before the keynote address, we're going to break for a bite to eat and the opportunity to chat. As I mentioned before, if you haven't had a chance to have a look and visit our IDS displays, I encourage you to do so. The Royal Society staff will be coming around with delicious bowls of food, I am told, for us to enjoy. But in the meantime, get another drink, enjoy yourselves. I just ask if we could be back here for 8:15 for the plenary address. Thank you. Good, thank you. Could people make their way back to the auditorium, please? Okay, welcome back, everyone. So, we now move on to the second half of the evening, the keynote address. And as has become practice, we'll use this occasion to invite one of our very many distinguished alumni to share some thoughts and observations on their work and career with the rest of us. And thus, it gives me enormous pleasure to introduce Professor Philip Donoghue, who was a recipient of an 1851 Royal Commission Research Fellowship back in 1997. Details of Philip's distinguished career as a leader in the field of research of paleontology is set out in the event program. I won't therefore repeat it here, but personally, as a theoretical physicist myself, with a persistent fascination with the nature of time, I was particularly intrigued by Philip's entry on Bristol University's School Earth Sciences website, where amongst a number of interests, he lists a curiosity to combine classical paleobiology with molecular genetics, to calibrate the tree of life to time using molecular clock theory. Now, I'm hoping Philip will share a little of his thoughts on this subject this evening. Phil, we're thrilled to have you here with us tonight and very much look forward to hearing you present molecular paleontology. I know we're all in for a great treat. Ladies and gentlemen, Professor Philip Donoghue.
Thank you for the very kind invitation and introduction. Obviously, it's an honour to be invited back by the 1851 Royal Commission after so many years when I was a research fellow. But also, I'd like to thank the Royal Commission more generally for plucking me out of obscurity and setting me off on a career as an independent researcher while I was still doing my PhD, basically. And they did, in fact, more than anything else, encourage me to finish my PhD on time. And at the time, what I was doing was studying what I assure you was a hot topic at the time, not anymore. I was studying this group called the conodonts, which are a group of phosphatic microfossils. So there's some just there on the head of a pin. So they're typically about 1 millimeter in size or less. Nobody knew what they were, how they functioned, what organism they belonged to, and that was basically my PhD, working with a bunch of other collaborators, trying to understand their function, building models out, not through 3D printing, but actually with clay, and then producing what I thought were fancy movies by rotating the model on a cheese board. And there it is, preserved for posterity. But the main thing I was doing was basically trying to understand their structure and use that as a basis for understanding how they grew, and then make comparisons to other groups of animals that ultimately allowed me to conclude that they were the first manifestation of a mineralized skeleton in vertebrates, and basically challenge the conventional wisdom that the skeleton had first evolved as an external armor to fight off these fearsome kind of sea scorpions way back in the Paleozoic. Instead, they evolved in this kind of lamprey-like organism, which was a predator using its mineralized skeleton to raptorially consume other organisms. So that's what the Royal Commission allowed me to escape. And what they allowed me to do was to take a much broader view, investigating the evolution of the skeleton more generally. And the reason why you'd give a paleontologist money to do this is, well, first of all, they'll go away. But the other reason is because if you look at living vertebrates, they're divided between the jawless lampreys and hagfishes, the cyclostomes, which have no mineralized skeleton. And then there are the sharks and bony fishes, which have every aspect of the mineralized skeleton that we also enjoy. There are no kind of living intermediates between those two that you could study in terms of molecular genetics or anything like that to try to understand how the skeleton evolved over time. But there are lots of dead fish that lie intermediate of these relatives, living relatives, that you could use to perhaps try to gain insights into the evolution of the skeleton. And as it turns out, they record the sequential assembly of about 5 different skeletal systems that in living vertebrates have a different embryological basis. And the work kind of showed that the skeleton evolved piecemeal over time. And those different embryological systems are kind of a footprint of their distinct evolutionary histories. And I really loved this work because it allowed me to study these fossils almost like living organisms, because paleontologists get really excited when aspects of organisms that aren't normally fossilized get bits of soft tissue get preserved. But for me, the skeleton is this unexceptional form of exceptional preservation, where the tissues themselves are turned into instant fossils. Every aspect of the tissues, the cells themselves, or at least the shapes of the cells, are preserved in the bony tissue, the mineralized tissues that make up that skeleton. And you can infer the sequences of development within those tissues, and even see the shapes of individual cells and cell processes. This is a bit of the armor of a 450 million-year-old fish. And if you looked at a living equivalent and prepared them in the same way, that is badly, then they'd look much the same. So that's what I really loved, this whole idea that I could look at ancient organisms and study them almost as though they were living counterparts. And I was particularly excited by it because I was a physical scientist. I have no training in biology. I don't even have a GCSE in biology, and it forced me to kind of do all that self-teaching to learn something about how the skeleton develops. And it made me a much broader scientist. So thank you to the Royal Commission for that. But also thank you to the National Endowment for Science, Technology and the Arts, who were the other people who kind of intervened in my career. I got this letter in the mid-2000s from this organization, which I'd never heard of, that said, we like the work that you do. Would you like to do something different? Which is kind of damning with faint praise. But they basically put me through therapy for a year. I had a counselor to try and explore what it is I really, really wanted to do. And they connected me with these 2 wonderful human beings. That's Robert Kelch from the University of Bath, Anthony Graham from King's in London. And basically, they put me into a zebrafish developmental genetics lab alongside undergraduates and PhD students, working at the wet bench for a couple of years, trying to understand the genetic basis by which the skeleton, which I'd been studying in dead fish, how it developed. So it provided me with insights into the processes that underpin the patterns that I saw in the fossil record, and understood how those processes could have evolved over time, so developmental evolution, to explain the evolution of the skeleton. But it was also an important intervention at the time because paleontology had a bit of an issue with molecular biology. There was a very strained relationship because there was something of a molecular revolution going on. As a consequence of the development of PCR technology, it was possible to pull any sorts of genes out of any living organism that you wanted to, and you could use that to do all sorts of things. And much of those things were things that paleontologists thought were theirs. Their things to do. So, for instance, they tore apart the tree of life as we understood it, that had been built by paleontologists and comparative anatomists, and redrew it in light of molecular phylogenies based on the shared characteristics of gene sequences. They even had the audacity, using molecular clock methodology, to calibrate those phylogenies to time. That was in the neo-Darwinian new synthesis, the one thing that was given to paleontologists, again, maybe to tell them to go away. Go away, try and come up with a timescale that we can use to establish rates of evolution and modes of evolution. And then they even used comparative developmental genetics, the discovery that the same genes are responsible for similar features in extraordinarily distantly related organisms, as a basis for reconstructing ancient ancestors. So on the basis of shared transcription factors, they reconstructed the last ancestor of all complex organisms as being segmented, having a brain, an eye organ, a heart, and so forth on the basis of shared transcription factors. So paleontology was going through this existential crisis. You know, what is there left for paleontologists to do? But luckily I had a kind of a foot in both camps, in molecular biology and paleontology at that time, and I saw it not as a challenge to paleontology, but as a real opportunity. Molecular biologists were saying, here, have this. There's like enormous amounts of data, and we've developed these fantastic computational methods. Run, go with it, and do all these things that we've shown you can do. So that's where, with some colleagues from the US, who I'm very grateful to, kind of had this insight that there were 2 fossil records, right? Not just one. There's the geological fossil record that I was familiar with, but then there's also the genetic record, which is written in the cells of our body, and indeed the cells of all living organisms. You know, if we compare gene sequences from our own cells to those of our gut bacteria, their shared characteristics were present in the last universal common ancestor of everything alive today. It's an incredibly powerful tool that we can use to address traditional paleontological questions. Right? So it was a real opportunity. And it's it was a two-way, I saw it at least, as a two-way flow of information. We could use molecular biology and data to enhance paleontology, but we could also use paleontology to provide insights into molecular evolution and genome evolution. So, for example, I spent some time looking at the evolution of jawed vertebrates, and that's an interesting topic, believe me, because on that branch, somewhere on that branch, we know from comparative genomics that there was a whole genome duplication. So in one of our deep ancestors, our genome was duplicated, so we had 2 copies of every cell, of every gene, rather, that we needed. And those extra copies were useless, right? They were effectively redundant, and so they were available to mutate and accrue new functions that lead to new evolutionary innovations. On that branch, there's an enormous number of phenotypic characters, anatomical characters, developmental characters that were innovated, distinguishing jawed vertebrates from their jawless relatives. It's a much more significant jump than from between invertebrates and vertebrates, which is the kind of traditional divide within biology. And it all occurs on this one branch, between the cyclostomes on the one hand and the jawed vertebrates on the other. And so at the time, in the early 2000s, there was this prevailing hypothesis that genome duplication led to this deterministic jump in evolution, where all of those characters were basically precipitated in almost one step, over a very short time period. But even you know, well, not even you know that's like a biased perspective of evolutionary history, right? Because there's a parade of dead fish that lie intermediate of those 2 lineages, the cyclostomes, the living jawless fishes, and the living jawed fishes. And they might have something to tell us about the pattern of phenotypic evolution. So let's look at some of these fish. The heterostracans, they're a kind of a group of early armored fish that lived in the Silurian, so about 430 million years before present. Aside from conodonts, they're the first vertebrates to possess a mineralized skeleton, and they manifest all of the canonical skeletal, or most of the canonical skeletal cell types and tissue types already evolved very early in the lineage that ultimately led to jawed vertebrates, but telling us that they occurred early and all the rest of the features evolved sometime later. Right? So that's giving us some hint that there's not some episodic explosive pulse of innovation. If we skip ahead, just to avoid the tedium, to the galliaspids, there are another extinct group of jawless fishes, and they're the first vertebrates to have paired fins. You may be able to see those ridges that extend from the back of the head through to the tip of the tail in a paired axis that runs down the back of the body. They're the first vertebrates to possess paired appendages. But in this fish, they're the equivalent of both our arms and our legs. The differentiation between pectoral and pelvic appendages hasn't yet been established. But they're the first vertebrates to possess paired fins, which is a fundamental innovation, a part of the body plan of living jawed vertebrates. But galliaspids show that they evolved much, much earlier. Also, they're the first vertebrates with a mineralized brain case. They're the first ones that have mineralized cartilage. And in that brain case, we can see the gross anatomy of the brain. and we can see that the nasal organs, getting into real nerd territory now, the nasal organs are separate from each other, which is a big deal because those organs have to be separate during embryology to allow the forward migration of the cells that lead to the origin of jaws, that lead to the development of jaws in embryos. And so there's been this idea that you separate those nasal organs in the early embryo, you get the forward migration of cells, and then jaws just kind of happen. Galliaspids don't have jaws, but show a fundamental reorganization of the brain that was required for the later origin of jaws. And then if we skip ahead, I could go on all night. If we skip ahead to the placoderms, they're the first vertebrates with a mineralized vertebral skeleton. You know, most vertebrates don't have a mineralized vertebral skeleton, but placoderms are the first to possess that. They have a mineralized gill skeleton. They have not just equivalents of our arms and legs as a continuous fin, they actually have separate equivalents of our arms and legs. They have both pectoral and pelvic appendages. They also have successional teeth. They're the first vertebrates with teeth, and those teeth occur on jaws, showing that even jaws evolved outside of the group of living jawed vertebrates. So overall, all of those characters that distinguish living jawless from jawed vertebrates actually evolved over a long period of time along the lineage that ultimately led to the origin of jawed vertebrates. But it didn't happen in one explosive, instantaneous step. It took 80 to 100 million years. Yeah, and that's a perspective of evolutionary history which would otherwise be invisible to molecular biologists, but it's possible if you take a more holistic view that incorporates fossil evidence. This whole idea of an episodic pulse of evolution explaining the origin of jawed vertebrates is just an artifact of extinction. So more recently, what we've been working on is trying to understand the origin of eukaryotes. I have to be careful here because there's somebody in the audience who actually knows something about the fossil record of eukaryotes. So we're eukaryotes, right? So eukaryotes are a group of unicellular and multicellular organisms that have complex cells. They have a cell that contains a nucleus that separates the genetic material from the cytoplasm, and the cytoplasm, if you remember from GCSE, has a whole bunch of organelles, including the endoplasmic reticulum and all sorts of things that are very difficult to say after I've had a few Prosecco's. But in particular, they have a mitochondrion, which is the powerhouse of the cell. And our understanding of the origin of eukaryotes is extraordinarily controversial. Almost nothing is agreed upon, except for the fact that eukaryotes are known to be a merger between the two fundamental lineages of life, which are the bacteria on the one side and the archaea on the other, which is another kind of distinct group of bacterial-grade organisms. And they came together sometime in the distant past. And the hypothesis is that alpha proteobacteria amongst the bacteria provided the mitochondrion, which basically detoxified an aerobic environment for an anaerobic host, which was the archaeon, which was now having to subsist in a world where the redox state of the atmosphere had shifted from being oxygen-free to somewhat richer in oxygen. So as I say, that's just about the only thing that people agree on. There are at least 8 different main hypotheses to explain the sequence of characters. There are many, many characters that distinguish bacterial-grade organisms from their eukaryote relatives. And they're largely distinguished on the basis of those little kind of purple tic-tac-shaped things, the mitochondria, whether they were acquired very, very early in the evolutionary history of eukaryotes, or whether they were acquired very late. And they're distinguished in terms of their order of acquisition relative to other features like a cell skeleton, the endomembrane system, a nucleus, and so forth. And all of those different hypotheses can coexist because there's basically no data, right? Because they are just different hypotheses that are based in different arguments of plausibility about whether you need energy to supply all of the innovations that eukaryotes invent, or whether the energy system, the mitochondrion, can be acquired much later. So as a paleontologist, I would really love to say that there's this amazing fossil record that actually shows the gradual acquisition of these characters, because there are no living intermediates between the bacterial-grade organisms and their eukaryotic relatives. But there isn't, I'm afraid. But what there is a whole series of individual gene duplication events that occur both on the archaeal lineage and the bacterial lineage that ultimately leads to eukaryotes. And so what we alighted upon as a research group was the idea that we could borrow an idea from paleontology and try to use these genes whose functions we know are responsible for eukaryotic inventions or innovations. If we can establish the order in which these genes duplicated, then we can understand the order in which those eukaryotic innovations were acquired in evolutionary history. And the way we do that is using molecular clock methodology, which is a kind of a speed equals distance over time kind of approach to working out evolutionary rates, and then using those inferences of rates to calibrate genetic distances to time. So it works on the basis that if you take the same gene out of two different organisms, like a bacterium and a human, then, and you align them like rows in an Excel spreadsheet, then they'll show many, many similarities, even though those organisms have been separated for billions of years. Many of the individual nucleotides will be unchanged. But depending on whether, in my example, they shared a common ancestor a long time ago, or more recently, there'll either be lots of differences or very few differences. If you know when those two organisms last shared a common ancestor, like there's a really good bit of fossil evidence for a particular comparison between species, then you can work out the mutation rate. And once you have that mutation rate, then you can apply it to inferring the time of divergence between the first pair of species and other species, which you add to your analysis. So that's the basis to the molecular clock. It gets more complicated than that inevitably, but that's all for nerds, not for you. And so this is typically what one of these gene trees looks like a genealogy of a gene that evolved on this lineage that leads to eukaryotes from their bacterial relatives. So there'll be a single copy, that single branch on the far left-hand side, from the bacterium, but then animals and plants will have two copies. Yeah? And they have two copies because the last eukaryotic common ancestor, or LICA as it's known, LICA also had two copies. And it has two copies because that single ancestral gene inherited from bacteria duplicated, just as a copy error, and the genome ended up with two copies of that gene. So if you can date the timing of origin of those two genes, you can work out when that one gene originated as a duplication, and then you can do the same for other pairs of genes. So we've done that. We came up with an overall phylogeny for the tree of life, as you do, and it gave us an envelope of time over which eukaryogenesis, the process of eukaryote evolution, occurred. And so it appears that eukaryotes diverged from their archaeal relatives at about 2.9 billion years ago, so deep in the Archean, but that the last eukaryotic common ancestor, so the last ancestor of all living eukaryotes, lived only 1.8 billion years ago. So the whole process took over 1 billion years, the assembly of all those features that make our cells much more complex than the cells in our in our bacterial relatives. And most of the genes, those are all, the histogram kind of shows, or the bar chart shows the ages of the gene duplications, and you can see in red, most of them are actually attributable to the archaeal lineage, and relatively few of them are attributable to the mitochondrial lineage, but you'll see also that the mitochondrial ones occurred generally much later than the archaeal ones. And the bars at the bottom are kind of the uncertainties on the time estimates for the duplication of those individual genes. And this data, believe me or not, is promising in that it suggests that these genes diverged at different times. They duplicated at different times. So we've done this for hundreds and hundreds of genes, which we know encode features like aspects of the nucleus formation, the formation of the cell skeleton, and are attributable to the mitochondrion as well. And what we can see, if we look at some of these, they're associated with the endomembrane system. Pointer doesn't work. Some of them occurred very, very early. Some of them occurred very late, and others occurred in between. So we can use those differences in terms of the estimates of the timing to determine the order in which eukaryotic features originated. And so in terms of hypotheses to test, there are many out there to test. And what our results indicate, in particular, is that the mitochondrion was one of the last features to originate. And there's no evidence for any other partners other than archaea and alpha proteobacteria in the process of eukaryogenesis. And so it tells us that all of those hypotheses are wrong. Which is great, right? It's science, right? Those are scientific hypotheses. They've been tested and rejected. So, and this is the sequence within which these eukaryotic features evolved. The actin cytoskeleton evolved very, very early. Aspects of the endoplasmic reticulum, Golgi apparatus, endomembrane system, and so on, all of those evolved prior to mitochondrial endosymbiosis, the origin of the mitochondrion. And in fact, the only feature that evolved after that we got insights into is sex. Sex evolved after the origin of the mitochondrion. Interesting, the timing of mitochondrial endosymbiosis, the mitochondrion being responsible for detoxifying an aerobic and oxygen-rich environment for ancestral eukaryotes, occurred just at the time when Earth's atmosphere flipped in redox state at about 2.3 billion years before present. So taking a bit of paleontological approach, using molecular data, we can leverage insights into one of the key transitions in the origin of complex life on Earth. So just one more story. What we've been working on again recently, we published it just last year, was not the origin of eukaryotes, but actually that fundamental origination event, the origin of LUCA, the last universal common ancestor, which is not the origin of life. It's just the last ancestor that everything alive today shared. It's as far as we can delve down into evolutionary history using molecular data. And there are many hypotheses. Obviously, people have been interested in this topic before. Many hypotheses to explain the nature of LUCA. People can't agree on whether it was simple or complex, whether it lived in a hot environment or a cold environment, and they can't even agree on whether it was cellular or some sort of an appetizing thin nucleic acid soup, right? So the very, very divergent hypotheses, and that's, again, because actually some of the methods available have not really been up to the job in terms of inferring the nature of LUCA. But surely, the goal of trying to infer this nature of the last universal common ancestor is a key goal for paleontologists. And so we should go out looking for fossils. People have found fossils. Problem is they can't even agree whether they are fossils or not. So there's an example from 4.3 billion years ago, deep in the Hageman. There are these kind of filamental features that are interpreted as iron-oxidizing bacteria. Even if they were fossils, we can't pin them to the tree of life, and so we can't work out their evolutionary significance, right? So unfortunately, the fossil record isn't helpful in this matter. But we can solve this paleontological problem using molecular data and molecular methods. So what we've done is we've leveraged the tens and tens of thousands of genomes of living bacteria and archaea to build a fundamental tree of life and date it to geological time. So our goal is to work out when LUCA existed, what its biology was, and what impact it had on the early Earth system. So using molecular clock methodology, which I've already bored you about, we estimate LUCA to have originated around about 4.1 to 4.3 billion years before present. There's some uncertainty in terms of that estimate, but it still tells us that LUCA, this organism, existed within about 200 or 300 million years of the moon-forming impact, which is fairly surprising. But it depends on how complex LUCA is, really. So to work out how complex LUCA is, what we did was to take that universal tree of life and use it as a framework for trying to work out the evolutionary history of all of the genes in the genome. So we took thousands and thousands of genes from living bacteria and archaea, and we used an evolutionary model that tries to control for all the different ways in which genes evolve. You now know, if you didn't, that genes sometimes duplicate spontaneously. Sometimes those duplications are lost, so the genes can undergo extinction. You can have new genes arising, and genes can also be horizontally transferred between entirely unrelated lineages. So we use this Ale model, which has been developed by one of our collaborators, that probabilistically reconciles all of those different competing mechanisms by which genes can evolve to infer which genes, or at least gene families, were present in the last universal common ancestor. And that allows us to infer that Luca had a genome about the size of a small E. coli, so about 2.7 million bases in terms of a circular genome, and that encoded about 2,600 proteins, right? Well, who cares? Well, what matters is what those genes were doing, and this is a reconstruction we have of Luca. It was clearly a cellular organism. We know that because there's a whole bunch of genes that are responsible for ether and ester synthesis and evidence for cytoskeletal actin as well, indicating that there was some sort of phospholipid cell membrane. We can even conclude that it was rod-shaped as a cell because it has this gene, MREB, which encodes a rod-shaped cell in living bacteria. We're able to demonstrate an entire pathway by which this organism could subsist as an organoheterotroph, as an acetogen, basically, feeding on CO2, and also there's evidence that it could live autotrophically, subsisting on hydrogen as well. There are entire pathways for synthesizing all of the amino acids and going from carbon fixation based on the acetogen metabolism all the way through to nucleotide synthesis. Perhaps the most surprising thing was the discovery that it had most of the components of an RNA-based immune system, so like CRISPR-Cas in modern bacteria, but without the CRISPR bit. It was capable of mounting an immune response to viruses using cutting and binding, telling us that even at 4.1 billion years before present, Luca was already embattled in a war with viruses. But there are no terminal oxidases telling us that it was an anaerobic organism. There's no evidence of photosynthesis or methanogenesis, which many people have argued were metabolisms of this ancient ancestor. So what we've done then is work with some Earth system modelers to work out if you plug those metabolisms into an early Earth system, a kind of a geochemical Earth system model, what does it do? Well, most of its products are acetate, and depending on which way you drive the metabolism, possibly CO2 as well. And on that basis, the Earth system modelers argue that it's fairly implausible that Luca lived on its own, given that its waste products would have served as a substrate for other metabolisms like methanogens. There's evidence that Luca lived in the surface waters, in that we infer the presence of a UV repair system as part of its genome as well. And so ultimately, we reconstruct Luca's living in the surface waters, living alongside methanogens, which are taking the waste products and then recycling them through a bit of photochemistry back to CO2 and H2, which it could have used as a basis for its own metabolism. So a very simple, low-energy yield ecosystem at about 4.1 to 4.3 billion years before present. So what this tells us is that Luca was a fairly complex prokaryote-grade organism rather than some thin genetic soup. And the complexity of that organism has to have originated super quickly, within 200 to 300 million years of Earth becoming habitable, and even that's debatable, which maybe suggests that some of the earlier steps in the evolution of life and to getting to prokaryote-grade organization are perhaps easier than other people have argued in the past. But more than anything else, I think it tells us that molecular biology and paleontology should get along together, that it's basically a winning combination. That paleontology allows us to see through the gaps in the modern tree of life, in that it gives us all these intermediates that we wouldn't otherwise know about, that refines our understanding of the evolution of genes and genomes. But also, molecular biology provides us with data and methods to see through the gaps in the fossil record. So I think, paleontologists should be overjoyed, but more than anything else, we have these two fossil records that provide for a holistic understanding of evolutionary history and this shtick of molecular biology as an approach to paleontology that I've been advocating for some time. So finally, I just want to thank the wonderful people who've helped me to do some of the research that I've talked about today, but also to thank you for listening to me droning on. But most of all, thank you to the Royal Commission for setting me off on this research journey and for funding research which is not useful in comparison to most of what you guys do. So, thank you.
Thank you very much indeed, Phil. Well, that was the most interesting, fascinating, boring and useless lecture I've ever heard. I mean, so, well done. I kept revising a different question I wanted to ask you, so I'm just going to pick one. I won't be too rude and take up time. Lucas, the origin of Luca, you're now taking it back to 4.2 billion years ago. I mean, it keeps going back further and further into the time when, you know, earliest life could possibly have started on Earth. Presumably that is saying that as soon as it was able to, it proliferated. And does that tell us something about the likelihood of simple life potentially existing elsewhere?
Yeah, I think so. It's actually getting younger. So we did a previous study that suggested it was a bit older than that. But we came up with a nerdy way of coming up with a more precise and hopefully more accurate date. But yeah, I think that's what it tells us. Either it tells us that life originated somewhere else, we've explored all of the crazy ways in which that could happen, and I don't think any of those are viable. But
well, Mars is the same age as Earth.
Yeah. And then there's, you know, the solar system's a product of a supernova, and our galaxy's only so old, and so on. But beyond that, yeah, I think it tells us that the difficult steps are much easier than people have suggested, and the probability of life, at least, probably not complex life, is more likely than many people think. Yeah.
Right, come on. I've got like half a dozen questions otherwise. Yes.
Yeah, I don't want any difficult questions.
Let's see how this goes. So thank you, really, really interesting talk. So there was some data you showed where effectively a lot of subcellular components evolved before the endosymbiotic event for mitochondria. Yeah. But a lot of those events need a lot of energy.
Yeah.
So how did that early cell gain that kind of energy, or ATP, without mitochondria? How did it fulfill the energy requirement?
Yeah, so it's that kind of plausibility argument that Bill Martin and others have put forward in the hydrogen hypothesis, that mitochondrion has to be the first step in eukaryogenesis. Otherwise, you haven't got enough energy to explain all these energy-hungry innovations. But data?
Fair enough.
Yeah, sorry, just to add on from that, do you think this shows that things have to evolve in a certain way? Or is it possible, in your opinion, that there's multiple routes of evolution in terms of the order of these organelles evolving in the cell?
I think it's really important that we carry on investigating these critical events in evolutionary history, otherwise I'm out of a job. Yeah.
Just also going off this point, if the mitochondria evolved so late and these evolutionary lineages seem to have, withstood the great bombardment, do you think that gives more support to life evolving in deep hydrothermal vents where there are energy systems they could tap into and they're perhaps more shielded from big impact events that occurred during this time period?
Yeah, so a lot of people have argued in the past that life couldn't have originated before 3.8 billion years before present because there's this period of late heavy bombardment. But that whole idea of a hypothesis of late heavy bombardment is predicated on a sampling bias of rocks on the moon by the Apollo missions, just from a very restricted part of the crust. And there's a lot of evidence to suggest that there may have been an increase in flux. My understanding, you probably know better, over that period, but it wasn't anything like people have argued in the past. And even if you do follow some of those old arguments, then it would only apparently boil off the top 2/3 of the world's oceans. There's still somewhere to live. So in Luca, we did reconstruct reverse gyrase, which is this thermotolerant gene.
But we've done some other work which shows actually, genes are built of domains that are a bit like Lego bricks, and that result is actually an artifact because the two domains, the two Lego bricks, have distinct evolutionary origins, one before Luca and the other one within the archaeal lineage. And then there's this complex history of transfer between archaea and bacteria in terms of assembling them into a gene. So because of that complex history, we end up with them being reconstructed in Luca because you take a gene perspective, but if you take a domain perspective, it's clearly not the case.
It's all in a cluster. You might as well with the microphone.
We've got one
there.
more over here, but do you want, there's one over your side.
Okay.
Okay, thank you. All right, so for a long time, the presence of oxygen in the atmosphere of another planet has been suggested as a signature of life because it's a non-equilibrium chemistry. What you're saying is that the evidence of oxygen might actually show that we've gone beyond Luca and therefore ready to bludgeon into a full diversity of life.
So there was no oxygen at the time of Luca. There was oxygens associated with the origin of eukaryotes, which occurred much later. But I think the key diagnostic features of life on a planet, people have argued based on remote sensing, is not oxygen, but oxygen and methane, which are in chemical disequilibrium. So if you have those in some sort of steady state, then you have to have oxygen being generated, you have to have methane being generated. Yeah, I can't remember where I was going with that, but it's good for the original premise, and that is it's not oxygen. Yeah.
Okay.
Hi, wonderful talk. I just have a question on LICA. You threw out all previous hypotheses, so I just wanted to know: are you proposing your own hypotheses? How would the alpha proteobacteria and the archaeal host get together? And do you have a fun, catchy name for your new hypothesis?
We do.
Oh, fantastic!
So it's difficult to convey. It is the most intensely debated topic in evolutionary biology, and people just simply don't talk to each other because they take opposing views. And so our new hypothesis is called the CALM hypothesis, which is the complexified Archean late mitochondrion hypothesis. So honestly, we started with the process and not the acronym. But
More questions? Yes. So two at the front.
Would you like to comment further on the fancy journal and the non-acceptance of certain articles?
Oh, yeah, it's in a fancy journal being reviewed, and I'm a pessimist, so...
Yeah. All right. I'm a humble astronomer. Astronomers actually borrowed this technique of phylogenetic trees from biologists to tie first-generation stars that enriched second-generation stars that enriched further onwards. As someone who doesn't study phylogenetic trees at all, when should I be skeptical of tying these generations together? Is there some sort of uncertainties or errors or when should I be skeptical of these claims that tie these generations all together? I think your ACE acronym comes into this, but yeah, I don't know.
So you don't need to be skeptical of mine at all.
Of course.
But I don't know how astronomers use them, but clearly there's a concept of genealogy there, where you get multiple generations of stars, but I don't know what data they use to analyze it or how they analyze it. But I'm going to find out now. It sounds exciting.
In your view,
Yeah.
does someone publish a result that you're skeptical of, and when do things break down?
So obviously.
Or is it always when you plug in your genetic code and you get the correct algorithm and everyone's like, yes, okay, this all works, we're
So we're in the Royal Society, and the Royal Society's motto is take no one's word for it. And so, yeah, everyone's skeptical of everyone's trees, but the overall structure of the trees, there is a coalescence in terms of lots of people coming up with more or less the same tree. There's some tricky nodes that people are discussing, but what we try to do in our work is actually date lots of competing trees to see how they impact on the inference of the clade age estimates. And we also use different evolutionary models, subsample the data in different ways, that kind of thing, trying to capture the uncertainty. So we end up with some of the timescales which are the least precise, but in my view, that makes them the most accurate.
So this evening has made me realise again how little I know about everything. So I started the last question that I asked about the sort of galaxies with. I didn't understand most of it, and it's pretty much the same with this one. But the question that I've got is rather more practical, which is my daughter really likes looking for fossils.
Okay.
And you started your talk about finding these microscopic fossils. How do people find them?
So, yes. So I actually had a slide here, which I pulled out because I thought it was just gratuitous. But it was clearly important. So there's me collecting some. So you basically, you go to the fields, the best kind of field work. You just take some lumps of rock that you hope contain them, and then you bring them back to the lab and dissolve the rock down, and then you use all sorts of like heavy liquids for separating out the different specific gravities of materials, and then you just pick through with a brush and a microscope.
It reminds me of, some in the audience will be old enough to remember when it hit the news that we'd found potentially fossilized microbe from Mars.
Yes.
And everyone thought, oh, we've seen life on Mars, and it turned out it wasn't a fossil, it was some crystal or some crystal structure. But I remember at the time, I think it was during Clinton's presidency, and there was announcements on the White House lawn that we've discovered alien life, and suddenly, the Vatican were going into meltdown. It turned out, false alarm. It's hard.
Indeed. But I think we need to get rid of that slide.
Okay, well, maybe on that note, we should draw this to a close, and please join me once again in thanking Phil for a fantastic lecture. So thank you again, Phil, for a hugely stimulating lecture and for fielding so many questions from the audience. So this does bring us to the end of what I hope has proved to be a fascinating and hugely enjoyable evening for everyone. So while I wouldn't dream of speaking for the more mature members of the audience this evening, I always feel, coming to these sorts of events, I always certainly feel rejuvenated by listening to some of our current fellows' research, and their enthusiasm, and to compare their projects with the work being undertaken now by some of our most distinguished previous winners. It gives a wonderful example of the possibilities and long-term influence enabled by the support of the 1851 Royal Commission. So many thanks again to all our presenters for their time, their commitment to this annual event. Thank you all for joining us. Thank you for everyone who's watching and listening online. Hopefully, we'll see you all again next year for what AJ mentioned at the very start. We hope to be a really particularly special event celebrating the Commission's 175th anniversary. Thank you all very much.